Hello viewers, in today's session we are going to discuss the concept of differentiation under the integral sign using this problem. So here we have to evaluate this integral that is from 0 to infinity e raised to minus 2x sine 3x over x dx, right? So let us start. So here let us first take this integral as say I1, right? And to evaluate this integral, we have to make use of the concept of differentiation under the integral sign. So what we will do, we'll introduce a parameter in this integral, right? So let us call that parameter as alpha. So let us write another integral which is a function of alpha. So we can now write I of alpha is equal to 0 to infinity e raised to minus 2x, and let us introduce the parameter alpha in the sine function, right? So we have sine of alpha x, right? And here we have x and dx, right? So the important thing about this method is that we introduce a suitable parameter to a suitable function, right? And we create a new integral that is I of alpha that is equal to this integral. So now the equivalence of this integral and this integral can be obtained by taking a particular value of alpha, and in this case alpha is equal to 3, right? So I of alpha, that is I of 3, is equal to our integral I1, right? Okay, so now the important thing is to differentiate this integral I with respect to alpha. So let us partially differentiate this integral with respect to alpha, because here we have x also, right? So what we will do, we'll take the derivative of I with respect to alpha. So we have di over d alpha is equal to del of del alpha, and here we have 0 to infinity e raised to minus 2x sine alpha x divided by x, and here we have dx, right? Now taking this operator, because del over del alpha is the derivative operator, so let us take this operator inside the integral sign, right? And here keeping x as constant, so we can now have 0 to infinity e raised to minus 2x over x, and we have del of del alpha, and here we have sine of alpha x, and here we have dx, right? So now the derivative of sine alpha x with respect to alpha is now equal to, here we have e raised to minus 2x over x. So the derivative of sine alpha x is x, and here we have cos of alpha x, right? Because the derivative of sine is cosine, and by chain rule the derivative of alpha x, that is del of del alpha of alpha x, is given by x, because x is we are taking x as constant, so we have del of del alpha of del here we have alpha, so the derivative of alpha with respect to alpha is 1, so we have x, right? So this is our x. So the purpose of introducing this parameter alpha is to get the derivative of I with respect to alpha, so that we can form a differential equation, right? Now here this x and this x get cancelled, so we are left with 0 to infinity and e raised to minus 2x, and here we have cos of alpha x and dx, right? So di over d alpha is now equal to this integral. Now we can simply obtain the value of this integral by using a standard result. So now we know that the value of the integral 0 to infinity e raised to minus ax cos bx dx is given by a over a square plus b square, right? So here we are using this direct result. So if we compare this integral with this one, then the value of a is 2, the value of a is 2, and this b is equal to alpha, right? So now the value of this integral using this formula, we have di over d alpha is equal to a over a square plus b square. A is 2, so we have here 2, and then we have 2 square plus alpha square, right? So this is 2 over 4 plus alpha square. So now we have created a differential equation that is di over d alpha is equal to 2 over 2 square plus alpha square. So let us solve this differential equation by using the concept of separation of variables. So here we can now write di, and we have 2 over 2 square plus alpha square d alpha. Now integrating both sides, we have integral of di, and here we have 2 over 2 square plus alpha square d alpha, and let us take the constant of integration as c. So now the integral of di is simply I, and here we can take 2 outside the integral. We have d alpha over 2 square plus alpha square plus c. Now to get the value of this integral, again we'll make use of a standard result. So the result goes like this: if we have the integral dx over a square plus x square, then the value of this integral is 1 over a tan inverse x over a, right? So here the value of a is 2, a is 2, and the variable x is alpha, right? So we have 2 times 1 over a is 2, and we have here tan inverse alpha over 2 plus c, right? Now this 2 and this 2 get cancelled, so now we are left with I is equal to tan inverse alpha over 2 plus c, right? So our integral I of alpha, that is I of alpha, is now equal to tan inverse alpha over 2 plus c, right? So now our aim is to get the value of this constant of integration c by using the boundary conditions. So now let us consider the boundary conditions as say alpha is equal to 0, right? So let us take alpha is equal to 0. So what we will get, that is I of 0. So I of 0 can be obtained from this expression. So when we take alpha is equal to 0, in this integral we have 0 to infinity e raised to minus 2x and sine of 0x, and here we have x dx, right? Now this term, that is sine of 0x, is the sine of 0, which is equal to 0. So our integral reduces to 0, right? So the boundary conditions are alpha is equal to 0 and I of 0 is equal to 0, right? So let us utilize these conditions in this equation. That is I of alpha is equal to tan inverse alpha over 2 plus c. So when we take alpha is equal to 0 here, we have I of 0, and here we have tan inverse of 0 over 2 plus c, right? So I of 0 is 0, so here we have 0, and this is tan inverse of 0 plus c, and tan inverse of 0 is 0, so we have 0 plus c, that is c, right? So the constant of integration is c is equal to 0 for these conditions, right? So now taking c is equal to 0 over here, so we have I of alpha is equal to tan inverse alpha over 2, right? So the value of this integral is equal to tan inverse alpha over 2. So now to get the value of this integral I1, we have I1 is equal to I of 3, right? So when we replace this alpha by 3, then we get I of 3, and I of 3 is our given integral, that is 0 to infinity e raised to minus 2x sine 3x over x dx, right? And I of 3 can also be obtained from this expression. So we have tan inverse 3 over 2, right? So the value of this integral I1 is given by tan inverse 3 over 2.